So we finished uh, comparing the physical properties of metals and non-metals. Now, if you see in your textbook, they have given you the physical properties of metals and non-metals in different paragraphs. If you see page 93, they are given in two separate paragraphs. But I showed you in the comparison form so that all of you, if it is easy for you to understand also to remember. When you compare things, no students, it's very easy to what you call understand and also to remember. So that's why I showed you the comparison form. Now we move on to the chemical properties of metals. Chemical properties of metals, especially metals. Okay. So let's see the first one: reaction of metals with oxygen. Again, this you have done in your 9th standard. Okay. So what happens when metals react with oxygen? Simple. So when metals react with oxygen, they will form their oxides. So metals react with oxygen to form oxides. Okay. So when you heat the metals in air, they'll react with the oxygen which is there to form metal oxides. Now sodium and potassium, they are highly reactive. We saw they are the most reactive, no? So they will react with the oxygen in the air even at room temperature to form respective oxides. Respective matlab the whatever the whatever oxides they have to form. Like sodium will react with oxygen to form sodium oxide, potassium will react with oxygen to form potassium oxide. But they are saying even at room temperature. That means you don't have to heat it. You don't have to heat sodium and potassium to make them react with oxygen. They'll automatically, when you expose them to the air, they will automatically react with the oxygen in the air and form the oxides. Okay, so you don't have to heat them. Whereas mostly other metals, you have to heat them in order to make them react with oxygen to form oxides. But sodium and potassium, they will automatically on their own spontaneously react with the oxygen in the air to form oxides. So this is the reaction for sodium. Sodium reacting with oxygen to form sodium oxide. Now we have to be careful whenever sodium is exposed to air, the sodium readily catches fire. So sodium, when you expose it to air, it catches fire. So that's why we usually store the sodium in kerosene. In the laboratory we store the usually other chemicals, we store them in bottles, no, in empty bottle we store the things in bottles, empty bottles. But sodium cannot be stored in bottles. One empty bottle also contains oxygen or air, so it will react with the oxygen which is there in the bottle and again catch fire. So to prevent them from catching fire, we usually we just no, sodium is kept in kerosene. Okay, and we'll see other reason why it is kept in kerosene, why it is stored in kerosene. One is for so that it doesn't catch fire. Okay, it doesn't come in contact with the oxygen in the air. Besides, sodium does not react with kerosene. Sodium does not react also with kerosene, nor dissolves in it. Okay, neither does it dissolve. So does not react also, does not dissolve also. So two things. So two more reasons why we keep it in kerosene. And the fourth reason, sodium sinks in kerosene. Sodium will sink in the kerosene. Why? Because if the sodium was to float on kerosene, what will happen if sodium floats on kerosene? Again the same story. The sodium, if it floats on kerosene, it will come in contact with the air, and in the air what is there? Oxygen. And the sodium will react with oxygen to catch what? Fire. So the sodium will catch fire. And to make matters worse, kerosene also is an inflammable liquid. No, whenever you want something to burn quickly, we throw kerosene on that. No, whenever you want the wood, no, the wood to burn faster, we put kerosene on the wood. So same way, if the sodium catches fire, and if it is stored in kerosene, and if this sodium catches fire, the kerosene also will catch fire, and it will make matters worse. The fire will become worse. So that's why we thankfully, thank God that what is that, sodium sinks in kerosene. Sodium sinks in kerosene, and therefore to prevent accidents, sodium is kept under kerosene. So remember this. So you'll have this give reason. Sometimes they ask you this give reason in the exam. Why is sodium kept under kerosene? Okay, so the simple reason is to prevent accidents. Okay, to prevent accident. The main reason is to cut off the supply of sodium with the air, because in the air there is oxygen, and the oxygen and the sodium will react and catch fire. So that is the main reason. That's why you keep it in the kerosene. Okay, because if it comes in contact with the air, what will happen? There will be accidents. There will be accidents. Now, oxides of metals, they dissolve in water to form alkalis. So whenever you take a metal oxide and you put it in water, it will dissolve to form a alkali. Now, alkali means what? In simple word, alkali means, you learned last year, alkali means base. Alkali is nothing but base. But alkalis and bases, there is some difference. Huh? Both are not the same. Alkalis and bases are not the same. What are alkalis? Alkalis are those bases which dissolve in water. You learned about acids, bases, and salts, no? So I'm talking about the bases. So bases which dissolve in water are called alkalis. So these metallic oxides, okay, this metallic oxide generally they dissolve in water to form alkalis, or what you call bases. So all alkalis are bases, but all bases are not alkalis, because not all bases are they dissolve in water. Okay, remember this. All alkalis are bases, but all bases are not alkalis, because not all bases dissolve in water, but all alkalis definitely dissolve in water. Okay, this is the reaction. So sodium oxide, when you put it in water, it reacts, or it dissolves in water and reacts with water to give you sodium hydroxide. Sodium hydroxide is a what? It's a base, because it has got a hydroxide. The word hydroxide, whenever you hear the word hydroxide, you remember it's a base. It's a base. We continue the chemical properties of metals, especially the reaction of metals with oxygen. Okay, we continue with that. We are still not done with that. We continue with that. So we come on to magnesium. Magnesium does not react with oxygen at room temperature. So like sodium and potassium, they do not spontaneously react with oxygen at room temperature. We have to heat them. So when you heat magnesium in air, it burns in air with intense light to form magnesium oxide. This reaction you have learned in your lower class also. No? When a magnesium ribbon is burnt in air, no, it burns with a white glow or white light to form a white powder of it burns with a bright light, no, to form a white powder of magnesium oxide. So it forms a white powder of magnesium oxide, but you have to heat it. It is not like sodium and potassium. Sodium and potassium, we don't have to heat it. Automatically it reacts with oxygen in the air without heating and forms the oxide, no, sodium and potassium. So this is the reaction. Magnesium reacts with oxygen to form magnesium oxide. Then we go to zinc. Zinc burns in air only on strong heating. See the word. Magnesium, you just normal heating, it reacted with oxygen to form magnesium oxide. But zinc, you have to heat it very strongly, very strongly. Then only it will form zinc oxide. Okay, and again zinc oxide also is white in color. So the reaction for zinc oxide formation, zinc plus oxygen giving you zinc oxide. Next you go on to iron. Iron does not burn even on strong heating. So like zinc, at least on when you heat it strongly, it reacted with oxygen to form zinc oxide. But iron does not burn even on strong heating, no matter how much you heat it. So what do you have to do if you want to convert the iron into iron oxide? The iron filings, you have to burn them vigorously. They burn vigorously when sprinkled in the flame of the burner. That means you have to throw the iron powder or the iron filing. Iron filing means small iron powder. So you have to throw the iron powder in directly into the flame of the fire, and then it will react with oxygen to form the oxide. So here is the reaction. Iron reacts with oxygen to form Fe3O4. Now Fe3O4 is a not normal iron oxide. It is an oxide of iron, no doubt. This is called ferrosoferric oxide. It is called ferrosoferric oxide. Okay, not ferric oxide, not ferrous oxide. Okay, you have heard about ferrous oxide, you heard about ferric oxide. This is ferrosoferric oxide. Okay, ferrosoferric oxide, but that is also a type of iron oxide only. So you saw know how you can see magnesium on normal heating reacted with oxygen to form magnesium oxide. Zinc, you have to strongly heat it, then only to form the zinc oxide. What about iron? Iron, even on strong heating, it did not burn. So what happened? You have to throw it directly into the flame of the fire. Only then it reacted to give you iron oxide. That is a ferrosoferric oxide. So yeah, okay. Now most metal oxides are basic in nature. and insoluble in water. Okay, but some of them, as I told you in the previous slide, they dissolve in water to form alkali. They dissolve in water to form alkali. Why we say most metallic oxides are basic in nature? Simply because when you put any metal oxide in water, you will get a base or alkali. You get a base or a alkali. So sodium oxide plus water gives you sodium hydroxide, and potassium oxide reacts with water to give you potassium hydroxide. Same way, magnesium oxide, if you react with put in water, you will get magnesium hydroxide. So any oxide of what you call any oxide for that matter, when you dissolve in water, will give you the corresponding hydroxide of the base. So I hope this is clear to you, students. So we now move on to the next property.